Right, so we're going to talk about the final aspect of flip-flops today. Um, just a reminder about the behavior of the SR flip-flop very quickly. How the SR flip-flop behaves. Um, not that one, this one over here. Um, you have your two inputs, S and R. S controls Q directly. R controls not Q directly, right? Now the major focus is actually placed on Q, on the output Q itself, right? So when Q is at logic 0, the circuit or the output of the circuit is set to be in a reset state, right? You could set that bit, you could set Q to be logic 1 by, of course, controlling it with the input S here, right? So right now, as it is now, Q is at logic 0. Let me start the simulation. Q is at logic 0, so I could set a bit to output Q using output S, right? So if I ensure that R is low, then I change S from low to high, right? That now will set a bit to the output Q, right? Now, if I change back S to logic 0, it isn't going to affect the output Q, right? Now, R itself now directly controls not Q, good? But if we just place our focus on what is happening with just remove that one there. We just want to place our focus on what is taking place with the output Q. Okay. Right. Right. So here it is in the reset state. So I could set a bit over there. I could set that to logic 1. When I put this S back to logic 0, Q remains at high output. I could reset the state of Q using now the input R. In that case here, I toggle R, well, I change R from 0 to 1 while S is at logic 1. Okay. And that there will reset the output state of this flip-flop or this latch in this case here, right? Now this is the flip-flop here. We could modify our SR, basic SR latch like this over here to have it behave in the same way that flip-flop I just showed you all would behave, right? Now this race conditions have been set up here, so I could eliminate that race condition by doing that, right? So this is S, this is the output Q that I'm focusing on. Let me remove that one there, right? So right now it is in a set state, so nothing I do to this here is going to affect. So this is the output S. Nothing I do to S is going to affect that output there, Q, the one on the top, right, on the output side, right? Because it is already in the set state, so nothing I do to S will affect it. Whether I change S from low to high or high to low, it doesn't matter. However, though, if I put S at logic 0 and I toggle R from 0 to 1, good, it should reset this output here, Q. It should reset it to logic 0, right? So let's see if that happens. Oh, the simulation is running, apologies. Right, so let me set up it here. Right, so it's in the set state. Right, so again, well, the simulation wasn't running just now, it's running now. So you see it's currently in the set state, and nothing I do here is going to affect it. However, to keep that at logic 0, I could reset this output state over here by using this input below here, which is the input R, right? I took off the ref des and so on, right? So the circuit is now in it. So the output of the circuit is in the reset state. So R had been used to reset the circuit over there. So again, once you do that, you lose control of it with this particular input. S is now controlling it. So I could now go and take S and set a bit over there, right? So that is your SR behavior, right? Now, as I've mentioned already, you could still put this circuit into a race situation where either you cannot predict what the output is going to be, or if you check to see which input signal reaches first, that determines what the output is going to be. That's why you call it a race condition, right? Now the SR flip-flop could be modified in such a way that you cannot possibly set up race conditions in it, right? So when you modify, I'm not going to show you all the modification, right? But when you when you modify it in such a way, sorry, it could be modified in such a way that you cannot possibly set up race conditions in such a flip-flop, right? So that modification of the SR flip-flop, whereby race conditions cannot be set up, is what you call a JK flip-flop, right? Now the JK itself is actually named in honor of the engineer who designed this circuit here. I think it was Jack Kilby, right? So the JK there, it doesn't have anything to do with the action of the circuit. It's named after the engineer who designed it, right? So anyway, so in the JK flip-flop now, you cannot set up race conditions on the output side, right? Now this one is fairly sophisticated, right? Because, well, I'm obviously using multisim here, right? Let me just go back to this previous design and stop that simulation there. As I was saying, you can't set up race conditions here. Now on the, I just want to talk about these two inputs here. Typically, we wouldn't, you know, if we are drawing a block diagram or whatever to answer a question, we wouldn't put these two controls above and below here, right? Now they have it as set and reset. Yes, it behaves like the set and reset we were talking before, but this is really preset and clear, right? Now these here are independent of these above and below, are independent of this input side of it here. This here is actually used to well, as I said, preset and clear. It is used to actually set the outputs before you go and perform any operations with the input of the circuit. So this here controls the output directly and independent of these inputs here, right? So these are like basically master controls, right? These master controls now could be used to set a particular bit or put the output into a particular state, right, that you want, let's say, before you commence operation with this particular piece of equipment here, right? So I could demonstrate that here, and it behaves just like the SR latch, right? So I could so right now this is Q and Q is at logic 0, so the circuit is in a reset state. So for me to set that output now, I just change that from logic 0 to logic 1, right? And I have preset an output bit, right? So this is preset and clear. Clear is when you remove logic 1 from output Q, right? So these are not really the inputs that we are going to how to say, to play around with when we look at the operation of this here. The purpose of these two is just to preset what the outputs are before we begin to operate the circuit itself, right? So if I want to clear that particular output there, I will have to toggle the clear or the reset terminal here, right? Good. So you could control the outputs directly from these two here, right? Right. Now, as I was saying, the JK flip-flop, you cannot set up race conditions in it, right? Now what it has an extra input here. So where you have S and R from before, that is now replaced with J and K, right? So forget about this reset and set above and below here, right? Those are separate. Stop. Right. Now, to prevent race conditions being set up here, you have the introduction of another input here known as a clock input, right? Now, how you know a clock input when you have a block diagram is it has that little triangle thing there, right? So that, you know, whenever you see a block diagram and that is there, they have that little triangle there, that is a clocked input, right? Now, a clocked input means that it is coming from some external trigger. That trigger could be varying high, low repeatedly, right? Of course, it doesn't have to be a signal that actually changes with time. It's something you could control yourself, right? Now, in the JK flip-flop, what actually has control of the circuit on the input side, and remember, I'm ignoring the set and reset above there, right? Typically, we don't put them in, right? Anyway, now, so the circuit, the outputs of the circuit are actually controlled by the clock, right, in the JK flip-flop, right? So J and K don't really control the output of the clock, right? So I have my simulation running, right? I have input J and input K here. The circuit is in reset state because Q is at logic 0, right? So typically, if it were an SR flip-flop toggle in this one here, would have changed that output, but the simulation is run. Okay, but that doesn't happen. J and K are actually no longer controlling the circuit. What is actually controlling the circuit is the clock, right? So if I toggle the clock, it should change. However, though, the clock only controls the circuit when J and K are both enabled. So I have to put J and K at logic 1, and only then can I control the outputs with the clock itself, right? Now, the reason why you would have a single input control in the clock, a single input control in the output of this particular thing there, even though there are so many input terminals, right? When you use a single input, that is when race conditions cannot be set up during operation. That's one thing. And also, too, it is not possible to put the output into an undesirable state, right? Now, you could use these preset and clear buttons over here to put that into an undesirable operation, right? So, for example, if I turn them both on, those two outputs will turn on, right? So you could do that with those master set and resets, right? But on the input side, you cannot do that. Good. So anyway, so if I turn J and K both off, right, I could control, well, sorry, I would not be able to control the outputs with the clock, no matter what I do to the clock. But if I turn them both on, then I will be able to control the outputs with the clock, right? Now the clock is currently on logic 1, meaning high. So I'm going to change the clock from high to low, and I want you all to observe what takes place on the right-hand side, right? I would spoil the fun a little bit. Nothing should happen on the output side, right? When I change the clock from 1 to 0. So let's look at that. See, nothing happened, right? Nothing happened. So now I'm going to change the clock from 0 to 1. And what should happen is the outputs will change now, right? So this particular setup here, the JK flip-flop, controlled by the clock, is a rising edge triggered output, right? So the outputs are only toggled when the clock goes from low to high, right? Now remember, you cannot put this particular thing here. When you control it with the clock, you cannot put it into an undesirable output state. So I cannot make both of them both on by using the clock or J and K, right? So I'm going to turn the clock on, and those outputs should toggle, meaning Q will turn off. So I basically put the circuit into a reset state, but at the same time, not Q will turn on. So that is what should happen when the clock turns on, right? And it does happen. So I'm going to turn off the clock now, right? Meaning the clock is going to go from high to low. Nothing should happen. But when I go from low to high again, it should toggle, right? So you cannot use the input side of this circuit to put this into an undesirable state. You cannot put this circuit into race conditions, right? Now the JK flip-flop itself could be used to construct any other flip-flop, right? So the JK flip-flop is like a universal flip-flop basically, right? So the clock controls the output. In particular, the clock toggles the output terminals. Both of them toggle, right? Now they're always opposite each other, of course. When the clock goes from low to high. When the clock goes from high to low, nothing happens, right? And I am demonstrating that. So only when the clock goes from logic 0 to logic 1 do you have the outputs switching, right? Now, because I want now the clock, now once you have J and K, either one of J and K off, nothing is going to happen, right? Now, typically you would either have both of them off or both of them on, right? So typically, this circuit here in the operation we are focusing on, you want J and K to either both be on or both be off, right? So what you would normally do is you would actually tie those two inputs together, right? So I'm going to remove this thing here. Oh, sorry, the thing is running. Let me stop that. I'm going to remove this connection here, and I'm going to take this and connect it up here, right? So I don't need this input again, because what I have now is one input controlling J and K. So if I do this, both J and K are on, and then the clock now, let me just shift the clock down a little bit. Sorry, I have to start back this simulation, right? Right, so the clock is controlling it once J and K are on. J and K are now controlled by one input, right? Once that J and K are off, the clock actually loses control, right? Now, this connection of the JK flip-flop, where J and K are tied together, is actually another flip-flop, a very specific operation of the JK flip-flop known as the toggle flip-flop or the T flip-flop, right? Now that there is not really in race conditions, right? What I have here is I have my clock connect the clock now, the input now is a square wave signal, right? 1 kilohertz in frequency, so it's going from logic 0 to logic 1. It's not really AC, of course, right? Because it's going from 0 volts to 2.5 volts or whatever it is, cycling between those things there, right? So that is not race conditions, okay? That is because the clock here is cycling at 1000 times per second, right? So that is not race conditions. Good. Anyway, so what I have now is I have a clock that is going to control itself automatically, right? It is set at a really, really high frequency, so we can't really see exactly what's taking place there. Yes, we are seeing that blink or whatever, but I mean, that is limited by the refresh rate on my screen and so on, right? Now, if I want to analyze the behavior of the input and output, I use something called the logic analyzer. The logic analyzer could be found on the right-hand side here. So if I double-click the logic analyzer, it's basically going to give me a graph of input and output, right? Not so much input and output, but it just gives me two graphs for those two particular terminals I'm interested in, right? So what I'm interested in here is well, even before I go into that, apologies, right? The JK flip-flop is tied, the inputs J and K are tied to one control. And when you do that, you create what is called the T flip-flop, right? So the T flip-flop is basically a JK flip-flop, which is essentially a very specially connected SR flip-flop here, right? Where it has one input that you could control, right? Control in a way that either you are going to turn it on or you are going to leave it off, right? When the T input is on, the clock assumes control of the outputs of the circuit, right? Remember, this preset, I'm clearly not paying attention to that right now, okay? Right, so, yeah. So once T is on, the clock assumes control of the outputs. How does the clock control the output? Exactly as we described before, the clock toggles the outputs, right? Toggles the outputs whenever it goes through a state of rising edge, right? So it's a rising edge triggered flip-flop in this case here, right? Now, there's something I did not really mention before, but it's probably more appropriate to mention it now, right? The JK flip-flop, right? And of course, the T flip-flop, which is a derivation of the JK flip-flop. Those are what you call triggered bistables, right? In that they have two stable output states, right? Why do they only have two stable output states? Because we already said, I mentioned it already, that you cannot use J and K to take or make Q and Q prime opposite to each other. You simply cannot do it. So there is no such output state as, you know, Q and Q prime being both 0. That is not an output state of this particular flip-flop, right? 0 and 1 or 1 and 0 are the only possibility. So you cannot get Q and Q prime both being 0. You cannot get Q and Q prime both being 1. Right? It's simply not possible. Well, but that is when you are controlling it with J and K and the clock and so on, right? So it only has two stable states. So these here have examples of triggered bistables, right? Meaning that only two output states, or let's say two stable, I can use the word stable, right? Only two stable output states. So there's no race conditions, there's no outputs, you know, arbitrarily switching and that kind of thing. Only two stable output states, and the output states are Q being 0, Q prime being 1, or Q being 1 and Q prime being 0. Those are your only two states. So there's no 0, 0, there's no 0. There's no 0, 0 for both of them. There's no 1, 1 for both of them, like that, right? Good. And then, of course, triggered means that the inputs or the input clock triggers the output. Right, so the input clock triggers the output. So these are what you call triggered bytes tables, right? Good. So I was going to talk about and show you all now how the logic analyzer could be used to look at basically a timing diagram for this circuit here, right? So I'm going to start the simulation, and I'm going to go to the this here because it's moving too fast for me to see. So let me stop this here, right? Right? There probably is a way, but some other time I will investigate that myself, right? Can I invert these colors? Right. So this here on top here is my input clock, right? Oh no, I hope you all have seen that clearly. On top here is my input clock, right? Can I change? Yes, I could change this here. Right. A few more right clocks. The division like that there, right? So the one on the top is my input, The one on the bottom is my output clock, right? This is an internal clock that is built into the logic analyzer, right? Anyway, so if you look now at the shapes of those two graphs, right? If I try to measure the frequency of this particular thing here, I basically will just look at one complete cycle and just basically measure it horizontal, right? So if I take one complete cycle, I'm trying to trace out one complete cycle here, right? Probably I could do this. Just give me a second. Just gonna take that here and place it over here. Right, probably need to make it a little larger. Right. So if I look at this here, right, and I'm trying to get an idea of what the frequency is, or probably have to use a different color because of that. Right. So this is one complete cycle here. If I go like this here, this is one complete cycle there. Right? I need to go up now. That's one complete cycle there. But on the other graph, this similar shape complete cycle is this here, which is obviously what? Twice as wide. So the periodic time of the output of this circuit here is double the periodic time of the input. Am I saying that correctly? Yeah. Good. So it means now it has half of the frequency. So in this circuit here, if I were to remove the logic analyzer thing there, in this circuit here, the output, and remember we only really focus on the output Q, okay? The output Q is always, but the frequency of the output Q in the toggle flip-flop is always a half of the input frequency, right? Because as according to this graph here, the logic analyzer graph, the periodic time is double, right? So the T flip-flop, one of the applications, or the primary application of the T flip-flop, is what you call a frequency divider, right? It divides whatever input frequency you set, right? We didn't go about, actually measuring what the periodic time and frequencies are. We already know that this is set at 1 kilohertz, right? So if I were to measure this output frequency, I would get 500 hertz for Q itself. Of course, Q prime would have the same thing, right? So one of the applications of the T flip-flop is it is used as a frequency divider, okay? Now, you could also use that frequency dividing capability of the T flip-flop now to create what is called a binary counter, right? So I have the binary counter circuit set up already here. Let me try to zoom a little bit. Good. Right, this thing is anyway a little bit. Let me just kind of shift this around here. I want to shift all of that. I'll fix up that after. It's really just this here I want to kind of focus on. That could go all the way down. Right, good. So let me zoom in here now. So I'm bringing up this here. Right. So what I have here is I have 3 T flip-flops in cascade, right? So remember the flip-flop is controlled. The flip-flop is controlled by the clock when the input marked T is at logic 1. Right? So the clock could only control your circuit, right? The output of the circuit, that is, when the input T is set at logic 1. So what I have here is I have a single input bit here of 1, and that is applied to the T input of my 3 T flip-flops here, right? Now, I did use the set and the preset and clear functions of this here because I just want to be able to put my circuit into a certain state, right? So simulation is running. I just want to stop it. And what I want to do is I just want to kind of reset this entire circuit here. So I need to start the simulation. Break this here. Start the simulation, and I want to right taking. Oh, I'm using the wrong thing. Apologies. Right. So all of them now, all the outputs are right. So I use my preset and clear for that. Good. So if I want to set a particular output state, the preset and clear buttons could be used for that, right? Good. Good. So it's good. But when you are actually using the circuit itself, you use it with them at logic 0. Right, so I'm going to start the simulation. This is going to initialize with all the LEDs on. I'm going to ignore that, and then we'll proceed to record the binary numbers, right? So it will initialize with all on, and then it will start behaving what. So I'm starting with 0, 0, 0, 0, 0, 0. Then it switched to 0, 0, 1. Then 0, 1, 0. That's what I have now. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. And then it should change back now to 0, 0, 0. Okay. So I'm going to stop the simulation, right? So do we have the binary numbers there, those outputs? Now, let me just examine what's the binary equivalent of all of this. Of course, this is 0, right? Either way, any number system, that will be 0. This is 1. Then it goes to what? It goes to 2. But 0, 1, 0 is 2, right? This here is 3. Can I get a point now? 4, 5, 6, 7. Right? Well, we can't represent 8, of course, but to represent the binary number, you need 4 bits, right? To represent 8. So this is what is taking place here in this. Sorry, let's see. This is what is taking place in the circuit here. The outputs now could be interpreted in such a way that they are basically counting up in binary, right? So you start off with the circuit with it at 0, 0, 0. It then cycles to the number 1, then to the number 2, then to the number 3, then to the number 4, and so on. All right. Now, what that is really counting is the amount of rising edge clock pulses that are taking place over all the way here, right? Right. So let's try to analyze why it is the circuit behaves like that, right? So I already have it copied here. So I'm starting off with it in that state. Now I already mentioned that it initializes with these here being on, right? So I'm not going to talk about how we get to this state. The software just initializes with Q at 0 and Q prime at 1, right? So all of these initially were at 0 and 1. Now remember the T flip-flop toggles, that's what the T is for, toggles whenever the clock undergoes a rising edge, right? So the first clock pulse, right, is when the clock goes from 0 to 1, right? That's a rising edge. So this will go from 0 to 1, and at the same time, this will go from 1 to 0, which would explain now why this LED here would turn off, right? That LED would turn off. Good. But however, though, as this one here goes from 0 to 1, this clock also goes from 0 to 1. So it means that this changes from 0 to 1, and that changes from 1 to 0. If that changes from 1 to 0, it means that this LED is going to turn off now, right? I have to turn off that LED, yeah. But again, this is fed into the clock. So this clock also goes from 0 to 1, which means this goes from 0 to 1 and that goes from 1 to 0. So this LED here would then turn off like that. So that explains why, even though we initialized it, the software initialized it to be all of them on, the next thing will happen is that all of them will go to off. So that's the binary 000 that I had there, right? So let me clear it up a little bit and then investigate what happens next, right? So right, so we have it set up here, right? So the clock now, remember this here is constantly cycling between 0 and 1. So we get to this stage 0 0 0. Okay, now the clock now will then, well, it just had its rising edge, changing everything to zeros, right? In a way where it ripples throughout the thing, right? It ripples very quickly. We can't see when it happens, but all of them basically change to 0 there. So the clock now will be on a high. It will drop to low voltage and then it will rise back up to high. So when the clock now goes through from 1 to 0, nothing is going to happen because this flip-flop does not change output when the clock drops, right? When the clock goes through a falling edge. But any clock will now, again, if it is at logic 0, it will then eventually go back to logic 1. So when the clock does a rising edge, now look at what happens. Rising edge here, now this was at 0. All of these things were at, all of these things were at 1. And then these were at zeros. Okay, which is why the LEDs are off. When the clock goes through its next rising edge now, this will change from 1 to 0. This will change from 0 to 1, which is why this LED would turn on. So that LED there turns on. Okay, which is how we get, well, before I even say that, this clock here is controlled, the clock of the second flip-flop is controlled by the Q of the first flip-flop, right? But this clock, therefore, if you look at it, it did not go through a rising edge. It went through a falling edge. The clock going through a falling edge does not do anything to the outputs. So this remains like this remains like this. Well, if this doesn't change, that doesn't change, which means this remain there and this remain there as well. So these two LEDs just remain off. So we get to a 0 0 1, right? To go again, let me clean it up a little bit again here. Right, I ain't going to do this for all 8. You kind of get the point if you haven't gotten the point already. So this is where we are now. So this is where we are with 0 0 1. Right, so with 0 0 1, these are my current outputs here. This here is 1, that's 0. This is 0 1 0 1. The clock was at logic 1, right? That produced that change. The clock went from 0 to 1. Now, when the clock goes from 1 to 0, nothing happens. That's a falling edge. But any clock eventually will go through a rising edge again. So a rising edge in the clock is going to change this to logic 1 and change this to logic 0. So what happens to this LED? This LED here turns off. Turns off. Right? So I'm going to get a 0 in that first position. Now, this clock then would have gone through a rising edge now in this stage. So this would toggle to 0, this will toggle to 1. Oops, to 1. So this LED would turn on. So then I will get a number 1 there. But however, though, this clock would have gone through a falling edge, so nothing will happen with this. This will just remain at logic 1, this will remain at logic 0, which means that this will remain off. So that will be that there, 0 1 0. So again, I went from having 0, right, to having 1, to having 2, and so on and so on and so on, right? So that is essentially how this particular circuit operates, right? So we'll say here is the outputs, right? Give a binary, a 3-bit binary number, which which indicates the number of rising clock pulses edges on the input side of the first flip-flop number 1, right? So let's call this FF1. This is flip-flop 2. This is flip-flop 3, right? So FF1 toggles the outputs, of course, with each rising edge of the clock, right? FF2 toggles with each rising edge of Q from FF1, which does not toggle with every input toggle. Okay, right? So FF3 toggles with each rising edge of Q from flip-flop 2 itself, right? So only if Q goes from 0 to 1 do you have flip-flop 2 toggling, right? Only if Q from flip-flop 1 goes through a rising edge, only then do you have flip-flop 2 toggling. And only when flip-flop 2 goes, flip-flop 2 output Q goes through a rising edge, do you have flip-flop 3 toggling itself. It's like that, right? So these numbers here, these numbers indicated by these LEDs here, right? They basically count the number of rising edges that the initial clock here sends into the input side of flip-flop 1. So that's why you call this here a binary counter, right? So the toggle flip-flop, the T flip-flop, I don't know if I mentioned that before, right? But the toggle flip-flop, it has those two applications. It could work as a frequency divider, and it could also work as a binary counter itself, right? Now that itself, I spoke about the D flip-flop before. Well, I mentioned the D flip-flop before, but it actually is not on the syllabus itself, right? Good. So that's kind of more or less it for flip-flops itself. So that means when we meet again, it will be to move on to some other stuff.